Welcome. So we are discussing about uncertainty. That is how an artificial intelligence agent should behave in an uncertain situation. So let us continue our discussion. So so in today's session, we'll we'll be discussing about the language of propositions in probability assertion. That is how to represent something in an uncertain environment. Right, so there should be some language of representation, right? So that's what we are going to discuss. So basically it's a way of representation. So it is a kind of knowledge representation, but how do we represent knowledge in an uncertain environment? So that's the uh, objective of this lecture. Generally the variables in probability theory are called as random variables because they can take some random values. For example, you can consider these as random variables: total, die 1. For example, consider the case of two dice, throwing two dice. So, so the total of two dice that that can be treated as a variable, as a random value that will be stored in the random variable total. And the value of the first dice can be considered as a random variable die 1. And every random variable has a domain. The domain represents the set of possible values that it can take. For example, if you consider die 1, the domain of die 1 is the values from 1 to 6. If you consider the domain of total, the domain of total is, is a combination of die 1 and die 2, sum of die 1 and die 2. So it takes values like 2, 3, 4, 5 up to 12. It don't take value 1 because it is 2 dice. So it starts with 2. So minimum value will be 2. The domain of die 1 is anything between 1 and 6. And the domain of a Boolean random variable is true and false. It can take any one of these two values only, nothing more than that. So its domain includes only two values. So in so when we represent things using in an uncertain environment, we can also use propositions such as doubles. For example, you can say doubles equal to true. So again, this is in the context of this die throwing example. So when you throw two dice, if both the dice gives the same value, in that case we say it's a double. So for example, if die 1 also resulted in a 3, and if die 2 also resulted in a value of 3, then in this case it's a double. So doubles will be set as true, and that can be done by using this type of propositional statements. Okay, propositions can also take the values of true or false. For example, if there is a proposition of this form a equal to true, then it can be simply abbreviated as a or capital A or small a, whatever it may be, which means a is true. If a is false, it can be abbreviated as negation of a, which means a is false. Okay, and domains can also take some arbitrary tokens as values. That is, it need not be a value. It can also take, for example, here die 1. These are numeric values 1 to 6. Total also numeric values, and Boolean contains the domain as true or false. So it always need not be numerical value. It can also take some arbitrary token as the value of domains. For example, the domain of age can be juvenile, teen, and adult. Juvenile means childish, child, teen, and adult. This is a form of domain. So this is the domain for age. We can consider like this also. The domain of weather can be sunny, rainy, cloudy, and snow. Okay. And variables can also have infinite domains. So it's not that always you should have finite domains. So for whatever we have discussed, the domain is finite. Whether the domain of weather contains only 4 values. The domain of age contains only 3 values. The domain of Boolean random variable contains only 2 values. The domain of total contains only 10 values. The domain of die1 contains only 6 values. They are finite, but it always need not be finite. It can take also, the domain can also take infinite values. And these infinite values can be either discrete or continuous. Discrete in the sense they are like integers, right? 1, 2, all these are discrete numbers. Continuous means they are real numbers. There is no, they are continuous. They're like 1, 1.1, 1.2, 1.002, 1.1.20001. So there is no discontinuity here. Such values are called as real numbers or continuous numbers. Okay. And if you want to represent something like this, so in an uncertain environment, the uncertainty we are going to capture the concept of uncertainty by using probability theory. So if you want to represent something like this, the probability that the patient has a cavity, given that she is a teenager with no toothache, is 0.1. So if you want to represent this fact to the knowledge base, the probability that the patient has a cavity, given that she is a teenager with no toothache, is 0.1, can be represented like this. Probability of cavity, this pipe symbol represents given that no toothache and teen. That is, the person is a teenager and he or she is not having toothache. Then what is the probability of having a cavity? It is 0.1. Okay. Sometimes we may want to represent the probabilities of all possible values of a random variable. So that can also be represented like this. For example, if you consider the random variable weather, which can take any one of these values, either sunny, rainy, cloudy, or snow, the probability of weather to be sunny is represented as 0.6. The probability of weather to be rainy is 0.1. The probability of weather to be cloudy is 0.29. The probability of weather to be snow is 0.01. So when you add up all these things, you will get 1, right? So in a more simpler way, here we have represented different values of the probability of weather separately. Instead, this can be represented in a very simpler way, something like this. P of weather. Here this P should be represented in bold. This P should be represented in bold. P of weather equal to 0.6, 0.1, 0.29, 0.01, which means the probability of weather to take the value of sunny is 0.6. The probability of weather to be rainy is 0.1. The probability of weather to be cloudy is 0.29. The probability of weather to be snowy is 0.01. So this is just a simpler way of representation. For this, we should use this P in bold, right? So the bold P indicates that the result is a vector of numbers. So in this case, the result is what? Vector. It's not one value. Here it's a single scalar, right? Whereas in this case, the result is a vector. So it represents the values of multiple other things. Okay. And this bold P can also be used to represent conditional probability. Apart from representing the result as a vector, the bold P can also be used to represent the conditional probability. So probability of x given y can be written something like this. Probability of x equal to xi given that y equal to yi. So given that y is equal to yi, what is the probability that x will take any of these xi values, right? For each possible ij pair, right? Probability that y is equal to yi is given. Given that, what is the probability that x equal to xi for different values of I and j? So this type of probability is called as conditional probability. And these conditional probabilities can also be represented using bolded P. Okay. So for continuous variables, we cannot write the entire distribution as a vector because there are infinitely many values. So how do we represent the possible values that can be taken for a continuous variable? So we can define the probability that a random variable takes on some value x as a parameterized function of x. That is, we can, for example, we can say something like this. Probability of known temperature equal to x. Probability of known temperature to be x is to be a particular temperature. Probability of known temperature to be x is uniformly distributed over this interval. The probability of the known temperature being uh, it's a it's being the probability of the known temperature is uniformly distributed within this interval 18C to 26C, right, into x. Okay, so just a minute. Okay, okay, so the probability of known temperature uh, is uniformly distributed. So this statement basically says that the probability of known temperature is uniformly distributed between 18C to 26C, right? Here C represents centigrade. So this value, this known temperature value, the known temperature value is x. Okay, so x is uniformly distributed between 18C and 26C. That's the meaning. So which means that the known temperature will surely take the value between 18C to 26C. That's the meaning. The probability density is uniform from 18C to 26C, which means that it will surely take the value between 18C and 26C. There is 100% chance that the temperature fall in that 8C wide. 8C is 8 centigrade wide. Between 18 and 26, we have 8, right? The width. Okay. And 50% chance it will fall in any 4C wide region. So this contains two 4C wide region, right? So 18C to 26C, it contains two 4C wide region, 18 to 21 and 22 to 26. So so you can say that uh, the the value will the the known temperature will 100% fall between 18C to 26C. Okay, or otherwise we can say that there is a 50% chance that it will fall within this range, and there is another 50% chance that it will fall within this range, so on and so forth. We can keep elaborating this. Similarly, we can say that 25% of chance in falling in any of the 2C wide region, so on and so forth, right? Okay, so so we write the probability density for a continuous random variable x at value x as p of x is equal to x, or just p of x. The probability density for a continuous random variable x at value x is represented as p of x equal to p of capital X equal to small x, or just p of x. Okay. So the intuitive definition of the probability of x is the probability that x falls within an arbitrary small region beginning at x divided by the width of the region. So the probability density for a continuous variable x, okay, capital X, given that capital X equal to x is represented in such a way that the x will take, here x is not single x, please mind that the small x is also not single x, it has a small region, the x has a small region, range, some region it has. Okay, so x falls with an arbitrary small region beginning at x, starting at x, it has some range, some region. So whatever its range, that range divided by the width of the region. So that is how we calculate this probability of uh, small x, right? That is the probability or density of a continuous random variable x at value x. Are you getting? So x has a range. It's starting and it ends somewhere. So the probability of x falling within this range is its probability divided by the width of the region. So probability of x is nothing but limit dx tends to 0, p of x less than or equal to x plus further x is less than or equal to x plus dx. So this dx represents the range from x to where, the small range, divided by dx, because this is what this definition says. The intuitive definition of probability of x is the probability of x falls within an arbitrary small region beginning at x divided by the width of the region. Okay, so it's nothing but the probability of the probability. It's nothing but that it's nothing but the x fall. It's nothing but the probability that x falls within that small region divided by the width of the region. So that's what this equation says. So for known temperature, we have something like this. Probability of known temperature equal to x is it is uniformly distributed over 18C, 26C. So the value of x is distributed between 18C and 26C, right? And 100% sure we know that the known temperature will be between 18C and 26C, right? So for this case, the probability density is given as 1 by 8C. Is 1 by 8C is probability density value, right? So its value is 1 by 8C if the temperature is between 18C and 26C. Otherwise, it is 0. Okay. So if the range is between 18C and 26C, the probability density function is 1 by 8. It's not probability. Probability is 1 because 100% probability that 100% chance it is 100% true. 100% chance that the temperature fall in the 8C void, right? So it is the probability is 1. The probability density is 1 by 8C. Okay. Again, probability density is nothing but for a particular random variable x, if it can take value within a given range, then identify its probability. Its probability will be something, say k. Then k by this width, k by this whatever this width of this region. So that is nothing but the probability density function. So in this case, if you see, the probability that the known temperature will be between 18C and 26C is 100, that we know. 100 means it is 1. Okay, the probability value is 1. So it means what should we do? 1 by 8C, the width is 8, right? So 1 by 8C. Okay, otherwise it is 0. So in all the previous cases, wherever we are using C represents centigrade. It's not a constant, right? So if P of known temperature equal to 20.18C, okay, then which is equal to 1 by 8C. Here if you note that, yeah, as we already said, 1 by 8C is not a probability, it's a probability density. The probability that the known temperature is exactly 20.8C, this is 0. So this you should understand clearly. See, actually this 20.18C is the probability that the known temperature is exactly this one. Here we are not specifying any range. That's the problem. Here we are not specifying any range. We are saying that the probability should be exactly 20.18C. In that case, the probability is 0 because 20.18C is a region of width 0 because it don't have any width. Okay. So if you want to calculate uh, uh, using this type of technique, then surely we have to specify some width. So we can specify 20.18 to 20.25. So what's the probability of having the temperature between the known temperature between this? Like that we can ask, because here now now we have some probability for this. When you divide this by the actual width of the region, then we'll get the probability density function. So in this case, the probability that the known temperature is exactly 20.18C is 0 because 20.18C has a region of width 0. Fine. Now we also need some notation uh, for representation of multiple variables. We need notation for distributions on multiple variables. So to represent multiple variables, we can use comma. For example, P of weather comma cavity, which means that the probability of all the possible values of the probabilities of weather and cavity. Okay, weather is a variable, cavity is also variable. Weather can take values like summer, winter, autumn, spring. Cavity can take values true or false. So basically weather can take 4 values, cavity can take 2 values. So all the combination of this thing, that is what is the So that is what is called as the probability being distributed over multiple variables. So here all the possible combination can be represented using a 4 by 2 table. Okay. And this table is called as the probability distribution of weather and cavity. Here there is another example. The probability of sunny comma cavity would be a 2-element vector. See, here you should understand one thing. This sunny is represented in small letter, and this sunny is the value of a weather. Weather can take 4 values, right? Sunny, rainy, windy, and cloudy, right? So weather can take 4 values. Out of that, one of the value is sunny. So here what we are checking, what is the probability of having a sunny weather? This cavity, but it is not a value, it is a variable. So cavity can take value either 0 or 1. That is whether somebody is having a cavity or not cavity. So probability of sunny comma cavity means what is the probability that the weather is sunny and somebody is having a cavity. And then what is the probability that the weather is sunny and somebody is not having a cavity. Okay. So P of sunny comma cavity would be a 2-element vector giving the probabilities of a sunny day with a cavity and sunny day with no cavity. This sunny is fixed, cavity changes. So it gives an probability of a particular day which is sunny with cavity and again a sunny day without cavity, right? So the product rules for all possible values of weather and cavity uh, can be written something like this. So the product rules of all possible values of weather and cavity can be written as a single equation. Probability of weather comma cavity is equal to probability of weather and cavity. So all possible values of weather and all possible values of cavity is equal to probability of weather probability of weather given the probability of cavity. Okay, this is probability of weather given cavity, which means that somebody is having cavity. Then what's the probability of the weather? Actually, in the real world, there is no connection between cavity and weather. So this is just an example. Probability of weather and cavity is nothing but probability of weather given cavity into probability of cavity. So that's the formula, right? So now probability of weather and cavity can be represented in all these 4 styles. Okay, weather can take 4 values, cavity can take 2 values. So probability of weather, W is weather equal to sunny and cavity is equal to true. This is nothing but P of weather equal to sunny, cavity equal to true into P of C. What is P of C? That is cavity, right? So this is sunny and true. Similarly, rainy and true, and the other part is always P of C equal to true. Okay. Similarly, cloudy and true, snow and true, sunny and false, rain and false, cloudy and false, and snow and false. So these are the 8 rules that has to be added if you want to represent something like this probability of weather comma cavity. Okay, it is represented through this formula. Probability of weather and cavity is probability of weather given cavity into probability of cavity. Okay, so as a degenerate case, this is another example. Probability of sunny and cavity. Here actually there are no variables. There are no variables. Sunny is also a value. Sunny is a value for sunny is a value for weather. Okay, and cavity is also a value. Here it's, you can see it's not capital C. Capital C represents variable. Here it's not a variable, it's a small c. So which means that it is a which means that for cavity we are assuming that the value is cavity. That is, somebody is having a cavity. Cavity is true, right? So 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 basically this is a 1-element vector because here we don't have multiple values. It is a 1-element vector. That is the probability of sunny and both sunny and cavity. Somebody is having sunny, I mean the weather is sunny and it's also cavity. So basically it will give only one value, right? So that is the probability of sunny day with a cavity, which could be written as, so this can be written something like this: probability of sunny comma cavity, or probability of sunny and cavity. Okay. The probability of, what's the probability of having sunny and cavity? It can be represented like this: probability of sunny comma cavity, or probability of sunny and cavity. Now let us discuss like how we can perform inference using full joint distribution. Let us try to understand like how we can perform inference using full joint distribution. Okay. So the probabilistic inference, basically we use this for computation of posterior probability. Posterior probability is also called as conditional probability. So let us consider this example. This is a full joint distribution which is represented as a knowledge base. So this is what this table represents the knowledge base for full joint distribution, for an example with toothache, cavity, and all these things. Okay. So this column represents whether somebody is having a cavity or not. So this entire thing represents that the person is having cavity, and this entire thing represents that the person is not having cavity. Okay. And this part, it says that the person is having toothache, and this part, it says that the person is not having toothache. Okay. So this thing, it says that the person is having toothache, but also is having a catch. Catch means the instrument that was being used by the dentist, which was uh, uh, which has affected the uh, person a little bit. Okay. So catch is nothing but the dentist nasty steel probe catches in my tooth. So it got stuck in your tooth. So that is what catch means. So whether you experienced catch or not, that's what it means. So what's the probability that somebody is having either cavity or not cavity, and having toothache and having catch? So that's what this value, right? And somebody is having either they have cavity or don't have cavity, but they have toothache and they don't have catch. So that's the probability of this, right? Similarly, this is the probability that uh, the person can have either cavity or no cavity, but uh, they feel catch, and also there is no toothache. So that's the probability of this, right? And this represents that mm, the person is the person can have either cavity or no cavity, and they don't have toothache and they don't have catch. So this is the probability of that. Okay. So with this info, so the what is the probability of having cavity and toothache? What's the probability of having cavity and toothache? So that can be inferred from this table. So the probability that somebody should have cavity and toothache, so which is nothing but this is cavity, this is toothache. So only these two things, 0.108 plus 0.012. Okay. Probability of cavity. I think we are missing something. Yeah, we have this probability of uh, 0.108 and 0.012 probability of cavity, right? So we have to add all these things, 0.072 and 0.008. So this entire thing should be added up, 0.108, because this is what talks about probability of having cavity. 108, 0012, 0072, and 008. So that uh, hmm, yeah. So this is wait. So this is not just cavity; it is cavity and toothache. What is the probability that somebody is having cavity and toothache? So this is the probability that, sorry, it is cavity or toothache, not and. What's the probability that somebody is having cavity or toothache? Okay. So this is the probability for cavity alone. This is the probability for cavity alone. Okay. Now, what's the probability for toothache? This is the probability for toothache. But out of those probabilities, these two things has already occurred. So you should consider only 0.016 and 0.0064. So that's how we got all these things, 0.108, 0.0012, so on and so forth. So when you add up all these things, what you get is 0.28. So this is the probability of having a cavity or toothache, either cavity or toothache or both, right? Okay. So what is the probability of just having cavity? The probability of just having cavity is nothing but you have to add up the first row fully. So when you add up the first row fully, this is what the probability of having a cavity alone. So this you will get 0.108, 0.0012, 0.0072, 0.008. So the result is 0.2. This is the probability of having a cavity alone. So this type of probability is called as marginal probability, or this process is called as marginalization or swimming out. This type of probability is called as marginal probability, and this technique is called as marginalization or swimming out. So this can be, so here basically what we are doing, we are um, so probability of cavity in the sense, apart from cavity, what are the other parameters we don't mind? Other parameters can be anything. They can be either true or false. We just add up that. So that is the whole idea of the probability of cavity. So we want that we just check our state. We ensure that cavity is true, and then apart from that, the other parameters can be either true or false. Okay. So how? So this process is called as marginalization or swimming out. Now, how can we represent it through an equation? So probability of y. So you can assume instead of cavity as y, right? So probability of y is equal to sigma probability of y comma z. So y is already is here. This is what we are checking. Okay, but so but we should ensure that y is true. We should ensure that the probability of y is true, and whatever can be the value of z. Okay, that is here what we are considering. Only cavity should be true. Toothache can be anything. Catch can be anything. So the same thing, that's what we are representing through this equation. The probability of y can be cavity, is equal to what? Sigma probability of y comma z. Okay, and given that z belongs to, the small z belongs to capital Z. Okay, so so basically this whatever we are doing here, this is represented here because we are calculating probability of y, but we are not bothered about other probabilities. So that those other probabilities are represented as z. The other probabilities can be anything, right? So so in this example, for calculating uh, the probability of the cavity, okay, so basically what we did here, we have considered all the probabilities for which cavity is true. Apart from that, uh, basically we consider all the probability for which cavity is true, but the other parameters we ignored. The other parameters can be either true or false. Okay, so this is the rule. So this is a generic rule, and this is a specific rule for probability of cavity for uh, for for performing marginalization. So probability of cavity is sigma probability of cavity comma z. So the z can be anything. Now in this case, what are the possible values for z? Z can be either catch or toothache. Okay. So this rule is called as marginalization. There is a variant of this rule which is called which involves conditional probabilities, and this rule is called as product rule. So product rule basically it's a variation of the marginalization or summing out rule, and this rule is given something like this: P of y is equal to probability of occurring some event y is equal to sigma z probability of y given z into probability of z. Okay, so so the point is this is an example for uh, conditional probability. Okay, this is an example for conditional probability. The probability that the occurrence of y, a particular event, is sigma z probability of y given z into probability of z. So this is called as conditioning. This is called as conditioning. Okay, so we can also compute some important values with this knowledge. For example, we can compute the probability of a cavity given the evidence of a toothache. So probability of cavity given toothache. This is the formula. Probability of cavity given toothache is probability of cavity and toothache divided by probability of toothache. Okay. Now refer the table. What is the probability of having cavity and toothache? So what is the probability that somebody can have cavity and toothache? So this part is cavity and this part is toothache. So it is 0.018 plus 0.0012. So that is what our numerator is, 0.108 plus 0.0012. Now what is the probability of having a toothache? Now what's the probability of having a toothache? For that, just add up the first row, which we have already done here. 0.108 plus 0.0012, 0.072 plus 0.008, which is nothing but 0.2, right? So this is the denominator. When you divide, when you do this calculation, you get 0.6. So this is the probability of having a tooth, having cavity given toothache. Okay. Now let us also calculate the probability of not having cavity given toothache. What's the probability of not having toothache given not having cavity? The probability of not having cavity given toothache is, again, it is the probability of not having cavity and toothache divided by probability of toothache. So what's the probability of having not? What's the probability of not having cavity and toothache? Again, refer the table. The probability of not having cavity and toothache. There is no cavity, but the person is having toothache. What's the probability? 0.016 plus 0.064. So that's what we got, this 0.016 plus 0.064. The denominator is probability of toothache, which is nothing but, already we know, which is what's the value, which is 0.2, right? So when you divide this number by this number, what you get is 0.4. So here you can check. Here it is cavity with toothache. Here it is cavity. Here it is cavity given toothache. Here it is not cavity given toothache. So if you can see, this is 0.6, this is 0.4. If you add up, you will get 1. So which is a correct inference. Okay, fine. That's it for today's session. Okay, we'll stop here. Thank you.